I will warn you that I put a lot of jokes in this lecture.
It was late.
Just like my midterm.
I haven't yet had a chance to get there. I'm looking forward to having this long weekend. Maybe I can get some stuff graded. Get caught up on
Let's
this
just
stuff.
grade Aaron. Let's see how Aaron does.
So, okay. The title of this lecture, and it's not as obvious from this screen, but the tab has named it. The title of the lecture is Confidence. Not too much confidence. Just confidence. One must have it to give a lecture named it.
Well played.
Oh, he said, but not actually phasing the confident professor. Confidence is used in the common sense, although we do endow it with a mathematical definition to scare business majors who aren't actually impressed, but indifferent. Approximately. If, under some reasonable assumptions, aka probabilistic model, we estimate the probability of some event to be p%, we say we have p% confidence in it. Or no? I mean, business majors are all supply and demand. We'll call that a law. So I think we're even.
I'm not tracking.
There's like
Yes.
so many voices going on in your
I know, there are. They have a good time. Oh, you guys would miss it. So, we're back to computing probability from distributions. So we want to compute our confidence level in something. Then we need to compute a probability that something will be the case. So probability density functions and probability mass functions were how we computed probabilities before, right, of random variables. We said if you take the integral under the probability density function, or if you sum up the little bars on a probability mass function, then we get probabilities, right? If you take the integral over the entire random variable, then the probability density function integral is what? 1. Yeah. It has to be somewhere in there. It can't possibly not be somewhere in the entire real numbers if it's a real random variable. If it's imaginary, well, who knows? So, it's a thing.
Is it really?
Yeah.
What?
Terrifying.
Jordan?
Imaginary variables. I should do a class on quantum mechanics at the end of this.
Yes.
Because
I agree.
probability and statistics are like half of it, and the other part is differential equations. And then the other part's linear algebra. Like, you just take them all together and it's like, boom, quantum mechanics. Yeah. It's pretty cool. I recommend it just for fun. I mean, like, you can also really impress those business majors. They don't care. They don't.
Imagine if you're
No.
Johnny, you'd say you impress them women at the bars.
Yeah, I'm trying to not be all like, not to say that. In any case, what we're going to say is no.
That was a good response, by the way.
Okay.
That was an encouragement to move on.
Usually, we care most about estimating the mean of our distribution, right? That's like the number one thing that we want to know about a random variable. What is its mean? Because oftentimes a random variable represents something like, what is the temperature of something, or what is the mass of something? We want to know what the value is, not necessarily all of its random glory, but we want to know like what the mean is. Like what's the mean weight of this chunk of bile that we spewed over the weekend and let dry. So that was not planned. That one just came out. Believe it or not. like bile. Okay, so recall from the previous lecture that when several samples are taken, each with its own mean, the mean is itself a random variable, right? With a mean, of course, because it's a random variable, so it has a mean. So the mean is a random variable. It has a mean. Yes, that means meanception.
I got it.
Yeah. I even incorporated GIFs into this lecture. You're welcome. But more importantly, just kidding, equally so. Meanception is equally as important as this next thing. The mean has a probability distribution of its own, right? The central limit theorem, which we're not going to define in all of its glory, all we really care about is to be able to say to whoever, including business majors, from the central limit theorem, we know the following.
Did this major piss you off today or something?
No, I don't know. If you're going to make fun of somebody besides civil engineers,
You do that?
it's got to be business majors.
What about art majors? Next is art majors.
Oh, no.
Sociology
No,
majors.
they already
or
I actually, I have sympathy for them.
philosophy.
Because they're not going to make money.
They chose that.
The business majors are going to make all this money.
And pretend they know calculus.
And, yeah, exactly.
Okay, now I hate them.
So, yeah. Also, they tend to be like the smug ones. Don't know why.
Because
Figure
they
that
have
out
to
yet.
barely do anything to get the grade.
Ooh. Yeah, you like this joke? Okay. How many business majors does it take to screw in a light bulb? Just one, but they get 3 credits for it. That is a good one, right? Okay, sorry. I'm not, I really,
For those of you who are not laughing, evidently you get a better sense of humor.
yeah, apparently, clearly, that is the conclusion. So, the central limit theorem has as one of its implications that as the sample size n gets large, remember, sample is a bin of measurements that we take, right? So, as the bin gets large, or we get a lot of samples in each bin, or a lot of measurements in each bin, so our sample size n gets large, regardless of the sample distribution. So each bin could have its own probability distribution. But when you take the means of all these bins and you turn that into a random variable, strangely enough, the distribution of means approaches the Gaussian distribution. No matter what the original random process distribution was, which is weird. It's weird. It is not something that you would have expected. At least not something I would have expected. But it does explain why the Gaussian random variable is so ubiquitous. That's why people always like, oh, everything's a Gaussian. Well, that isn't exactly true, but if you're mostly concerned about the mean, which we mostly are, then the probability distribution of the mean is Gaussian if you have large samples. So, pretty cool. And I think what I would say is it's mind-blowing. Yeah.
Solid.
I like this GIF. I sometimes sit here and just watch this GIF.
You can't discover new things each time you watch it, so.
It is pretty cool. I don't know who made this GIF, but it's awesome.
Unless you have Netflix. There's alternatives.
Netflix doesn't have that. I've checked. No. Okay. So, but sometimes, sure, the central limit theorem tells us this. And sure, it's been proven by people. But sometimes I worry I'm being lied to. Or actually, more accurately, sometimes I always worry I'm being lied to. So let's check. So, let's do good old generating of some data to test the central limit theorem. Because we have the audacity to do that. We're like, okay, central limit theorem says this. Let's see if it's true. So, let's generate some data to test it. So data can be generated by constructing an array using a seeded for consistently random number generator. Let's use a uniformly distributed probability density function between 0 and 1. We haven't actually talked about this one before, so I'm going to draw it for you. Say you have a random variable that has, so a random variable x with values x. This is supposed to be lowercase, but it's not that big of a deal. And so I want to say, I don't want to put that as the other axis. What I want to do is I want to say this is the probability density function. So we'll use a uniformly distributed random variable in the interval 0 to 1. Well, I kind of missed there, didn't I? Well, okay. It's good now. So this is 1, and this is 0. And then this has to be, the integral of this has to be equal to what? 1. So if it's between 0 and 1, and the area of a rectangle is the base times the height, and we need that area to be 1, what is the height? 1. Wait. Lectures are better with GIFs, I think. Okay.
Is it GIFs or GIFs?
Oh, it's definitely GIFs. Okay. Yeah, I'm pretty sure.
Otherwise, you're talking about people.
It says everyone but the creator of the actual format. Yeah.
Oh my gosh, not now.
Who is it? Jeff? Spelled with a G? As if anybody in their right mind would spell Jeff like this.
I've met a G off, by the way, and I went to the zoo the other day and saw a giraffe.
Yeah. Anyways, enough about Jeff. All right. Any Arrested Development fans? Okay, good. I'm glad. Okay, so this is the probability density function, which means that if we were to just choose a random variable out of this box, it would have the same probability of being in any subinterval here, right? Because it's flat. It's not more likely to be in any one space than in another space, right? Flat distribution. Okay, so we're going to use that distribution for each of our bins, and then we're going to be like, okay, well, if you let n get large, does it still approach a Gaussian? Because if it started out with a Gaussian in each bin, I think we're all like, okay, like, sure, it turns into a Gaussian, like, big whoop. But if it starts out like this, and then the means are normally distributed, that's pretty cool. So let's try and see. I don't know. I'm a scientist. I'm objective about it. I don't care. I don't even care if it's true. Central limit theorem, doesn't bother me if it's not true. That's why we're testing it, right? All right, so.
Who are we to stand on the shoulders of giants?
That's right. I prefer to stand on my own shoulders. Okay. So. All right, so we're going to use this uniformly distributed probability density function between 0 and 1. And this is a little bit, so this is a simpler example than we used in the last one, because we had like this time varying sinusoid and all of that stuff. We're not doing that this time. We're just going to have a sample size of 150, which is large, right? Because the whole, central limit theorem thing says, oh, as n gets large, so we do have to have that part. And then we want to have several samples. Otherwise, the probability distribution just kind of looks like one bar, which isn't as fun. So you got to have more bars to make it look cool. So, yeah, so number of samples. And then, so we've got our population mean, which is going to be 0.5. I know that this is also a mind-blowing statement, but the mean of this is 0.5. Boom. Yeah. You know how you find that?
1 divided by 2.
Yeah, 1 divided by 2. You're right. So yeah, so it's actually, we did define the mean. There's an integral definition of it, but for this, it's pretty easy. So it's nice. Okay, so
I know what integral you're talking about. I just haven't used it in a while, so it's like, yeah, there is an integral method, but for the sake of time, it's probably
yeah. Well,
But isn't there a
I have a lot to talk about in this lecture. Otherwise, I would talk about that. We did define it though a few lectures ago, so I go back to it. Yeah. So seed the random number generator first. I seeded it with 11 because of Stranger Things, and everything is connected. You guys got to track. Everything is connected. Okay. So signal A is going to be our signal. All right. So the signal, and then I use this subscript A or the underscore A to mean this is an array. Okay. So signal A. I use this really nice random number generator function in MATLAB that gives me an n by m matrix of uniform probability density function values. So that's easy. Rand of n by m. Not rand of Paul, but rand of n by m. Atlas shrugged. So size of the signal is going to tell us what the dimensions are of this signal. And it comes out 150 by 120, which makes sense because n was 150 and m was 120. Okay, so let's take a look at the data by plotting the first 10 samples. So the samples are given in the columns, okay? So we said the sample size is 150, and we have 150 rows. And then the number of samples is the number of columns, okay? So each sample is given in a column. So so we'll plot the first 10 because I did this, at first I was just plotting all of them, and it got really gross because this is a lot of data. And it also started crashing the kernel a lot on this. It's not super stable to run MATLAB in this Jupyter Notebook environment, which makes sense because it's built for Python, but whatever. Okay, so let's plot 10 samples, and I'm going to use this. This is nice. So for anybody who has tried to generate a plot in MATLAB in a for loop, so that you go through every value in an array and do that plot, that's pretty fun to do. The thing that you almost immediately run into that's annoying is you want them to be different colors. And that sucks to make them different colors. Well, turns out that there's this really nice thing that I didn't learn about until not that long ago. This will give you RGB color. The jet function that's built in will give you RGB colors. So it gives you, so RGB is in columns. So it gives you 3 columns of RGB values, and it gives it to you with samples to plot long, so the argument long. So if you ask for like 5, it'll give you 5 RGB colors that are like spaced out nicely so that they contrast each other, which is awesome. So this, although this is kind of a simple little statement here, actually saves you quite a bit of work if you're going to be doing a plot in a for loop. So we can plot from j equals 1 to the samples to plot, so 1 to 10. We're going to plot all of the rows of the jth column. So first column, second column, third column. We're just going to plot it, and then so we're just plotting signals, so we don't give it any x values, if you will, because we are just going to look at each sample. Okay, just a sample. It's just the index of the sample. Sorry. Index of each measurement. So that's what we do. I probably should actually evaluate some stuff. There we go. Boom.
Whoa.
Crazy, right?
Isn't that a Death Cab for Cutie cover?
I mean, it could be.
You just took me back a decade.
So what we've got on the horizontal axis here is the index. So we go from 1 to 150, and each one is going to be randomly chosen with an equal probability of being anywhere from 0 to 1. And so these values do just that. Obviously, this isn't like a great plot. You probably wouldn't want to include this plot in a report. It doesn't tell you a lot, right?
Well, there's one of those in my report.
But it does kind of give us a feel. And it is really pretty, right? I think it's pretty.
I'm basically you. Wow, just like 2 weeks ahead.
Art with Aaron. I mean,
Yeah.
Never made mistakes.
So if you're getting this now, you're good. If you're getting it 2 weeks ago, you're even better. So, all right, great.
I'm sure it's a parent teacher.
And then this is something like we might see for continuous measurement data if we had a randomly distributed signal that we were sampling. We took 150 samples per batch, and then we put them in columns of a matrix. So this is what we might see. Okay. Now, let's look at a histogram of this. But like only the first 10 samples again, because it also crashes my MATLAB. Whoa! I like this one even better. This one's really cool. So what this is a probability mass function distribution, right? It gives you, so 0 to 1, it's got to show up in here somewhere. What is that game where like you put in something? It's
Plinko?
Plinko? Yeah, where like the thing jumps around and then it like settles down in something. So
This looks more like a blocus to me.
Blocus.
Locus?
Yeah. No, it was like, I can call it blocus because it's funny. But you're talking about the strategy game, you have the square pieces, you have them around. Yeah.
Huh?
You know, with blocks.
Well,
What was it? It was with like, the one I saw was.
it's like if you had a lot of Tetris that was like layered 3D Tetris.
Those hand gestures really explain it. Like
Yeah.
Jack Sparrow stuff.
Yeah. So, this is there's some opacity on here, but you can see that essentially each of these is pretty much uniformly distributed. It doesn't like there's no clumping in any certain area. They're random, so you will see like for instance this lavender distribution, like several of the values of one of the samples showed up in this range here between 0.4 something and 0.5, which is going to happen when you do something randomly. You're going to get occasional clumping, but overall pretty uniform. This is just to give us a feel for the data before we start doing some calculation with it, because it's going to be over quick once we start doing calculations. All right. Also, pretty. I should make this like I have a Facebook thing now where it disables my news feed, which is like seriously the best thing ever. Like, so you can get on Facebook, you can like post something if you want, but your news feed doesn't distract you for too long. Any amount of time is too long. I should make this like what do they call that, cover photo? That's pretty. Okay. Anyways, but like not with the probability thing because I don't want to scare the math majors. Or not, sorry, the business majors. Damn it, I messed up my own diss. Okay, so this isn't a great plot, but it shows roughly that for each sample, we have a pretty uniform distribution for each sample, right? I mean, is that not what that tells you?
I can't make a good decision. I would need to see each individual graph.
I mean, it's true. Probably we should. And in fact, if we wanted to just look at one, we could look at one.
Nothing happens between 0.68 and 7.
Yeah, dead zone.
Jerks.
I could show you like 2 on the plot. I should also show you like.
Why does it show us 3?
That's the overlapping, right?
Yeah, it's showing us because we have this opacity that's letting you see.
Nice.
You can scare them English
Sorry?
majors too.
Oh no, I figured it out.
Just kidding. English.
I don't make fun of. Notice that I don't make fun of the English majors. I don't make fun of the art majors because, like, they're following their dreams. They know they're not going to make any money, and they're still doing it. So I have respect for that. Business majors, I'm bitter. Okay, so we have this, but I wanted to do 10 because I thought 10 was cool looking. All right. Now let's do sample statistics. So let's check out sample statistics. We want the sample mean and standard deviation of each column. Let's use the built-in mean and standard deviation functions, mean and STD, right there. Mean is there. So we take the signal, and so the syntax is you put in the signal, which is a matrix, right? You want to take the mean column-wise because the sample is happening column-wise. So you want to take the mean down the column. So if you're in an Excel spreadsheet, you want that mean to be at the bottom of your column. It represents the mean of that column, right? I know you guys like Excel. I don't know if you like it. I hate it, but anyway. Mean of each column. So this is, the syntax is give me your matrix and then give me the dimension to take the mean over. So the first dimension is columnarly. Columnarly. I think so. And then if you did the second one, it would be rowly. It would take the mean row-wise. And you can also have higher dimension arrays in MATLAB too. So once you get to start doing arrays that are like 3 or 4 dimensions, then you're having fun, okay? The mathematical objects that those represent are called tensors. They're pretty cool. Anyways. So actually, yeah, so stress tensors, that is, so a stress tensor is an example of a tensor. Yeah. So they were great. I recommend tensors. Also, they hurt your brain. They hurt, but like in a good way. Okay. So standard deviation, also same syntax. You give it the array, and then you give it the dimension over which to take the standard deviation. So this is really nice. The mean and standard deviation functions that I defined in the last lecture were not able to do this with higher dimension arrays. It would just give it a vector. You can actually give this higher order arrays, and it'll take the proper mean and standard deviation, which is pretty cool. All right, convenient. Now we can compute the mean statistics. Both the mean of the mean, x double bar, and the standard deviation of the mean, which we don't strictly need for this part, but we're curious. We chose to use the direct. We choose to use the direct estimate instead of the standard deviation of one sample divided by the square root of the number of samples. We chose to use the direct computation instead of using this formula to estimate it, but they should be close, and you can verify that they are close. You can just compute it directly in this case. It was hard to do in our previous case. That's why we used the square root of n formula. So either one's fine. I mean, technically the way that we're doing it here is a lot more computation, but realistically, I don't do any of that computation. MATLAB does it. Oh, but it wants me to do this one first. There we go. So the mean of the mean is 0.4987, which is, pretty close to 0.5, if I do say so myself. And then the standard deviation of the means, SMU, I might add, is 0.0236. And remember from last time that the larger our sample size, the smaller the standard deviation of the means should be. The tighter clumped they should be, those means. Because if you have a better mean each time, they're going to get closer and closer to that mean. So if in each of your bins, if you have more measurements, the mean value of each bin is going to be closer and closer to the actual mean, right? So, to the population mean. So, if you looked at those means as being a distribution, if you have a larger and larger sample size, you're going to get a tighter and tighter clumping of your means, which means that your standard deviation of those means is going to get smaller. The truth about sample means. I decided to start writing headings for my lectures like clickbait, okay? So the truth about sample means.
The truth needs to be all caps.
Yeah, that's true. I should. What they're not telling you about sample means. Moms agree. Sample means.
Or students react.
Students react. Oh, yeah, that's a good one. 4 out of 5 men have found. Okay.
Based on the sample.
It's the moment of truth. Let's look at the distribution. So what we're going to do is we're going to plug in our mean array, and we're going to just ask for a histogram of it. Okay? What? Look at that. 0.5, and that looks pretty much like a Gaussian normal distribution to me. So where we get the clumping at the mean and the tailing off. Crazy, right? Crazy. They didn't even lie to us. Central limit theorem. Wasn't even making that up. So, this looks like a Gaussian distribution about the mean of means. So I guess the central limit theorem is legit. We are going to have to investigate this whole flat Earth theory, though. Sometimes I just get sad about.
The world.
Yeah.
What parts of it? All of it?
Just it's like the part where we sometimes do things that are seemingly kind of smart and intelligent, and then other times,
Darwin Awards.
woof, woof. There's a legit movement of people who believe that the Earth is flat.
Is it early 1900s we invent cures for the worst diseases known to man, and then we go 100 years later and people don't want to give out these cures to people?
Yeah, it always has something to do with the Illuminati or something. I don't know. Who knows? All I know is when I think about it too much, I get really sad. Oh.
People believe space travel isn't possible because there's no air in space, so that means there's no drag in space.
Ooh, nice.
There's no ether, so there's no.
So actually, physicists were debating about that for a little while back in the day, and then we did it.
Gosh, news, their law is real. Whoa.
Yeah, I know. You guys. It's sad.
Speaking
Speaking of Gaussian and probability, we already know how to compute the probability a value of a random variable x lies in a certain interval from a probability mass function or a probability density function. if it's a probability mass function, we sum them up, right? We did that a few lectures ago. It's a probability density function. I have to take the integral over an interval. And that's the probability that it lies in that interval, right? So that's what we do. This means that for sufficiently large sample size n, such that we can assume from the central limit theorem that the sample means are normally distributed, the probability of a sample mean value, xi, is in a certain interval. I didn't finish that sentence, did I? Period. The probability is given by the probability of a Gaussian distribution. So I'll fix that one. I really was building on that. This really took the wind out of my sails. Okay. Is given by integrating the Gaussian PDF. The Gaussian PDF for a random variable, which is the, remember, it's kind of weird because our random variable is the mean, the sample mean. So we're going to plug that in, so it looks a little awkward. But what we're saying is the probability density function for the sample mean random variable, which is actually the random variable we care about more frequently than not, is given by this function, where mu is the population mean and sigma is the population standard deviation. So, if we can say from the central limit theorem that everything is like a Gaussian, as far as as far as probability density functions of means, which is what we care about, then we can compute the probability that a given mean is a sample mean is going to end up in an interval from this Gaussian distribution. Okay? And that gives us the ability to estimate what our confidence should be that the value is going to be in a certain interval. Okay? And this is sort of like the fundamental way that we assign confidence values in most of engineering measurement, is by using this method and one that's very similar to it. So the integral of f over some interval is the probability value will be in that interval. Unfortunately, that integral is uncool. I should have a gift for that. But it's not cool. It would just be the Flat Earther website. Okay. It gives rise to the definition of the error function, which for the random variable being the sample mean is just this. This expresses the probability of a sample mean being in the interval from minus. It's kind of awkward, my notation here, and I think I'm going to go back and kind of tweak it a little bit. But the idea is that it's the probability that you're in some interval of the Gaussian probability density function. So if we have ourselves a nice Gaussian, which that is not very Gaussian. This looks like whatever that purple guy is that's like with the Hamburglar. Grimace. That's what it looks like. All right. So, all right. So this is our random variable. This is the mean of our random variable. This is Gaussian, a normal distribution. And we want to know, oftentimes, what is the probability that we're at the mean plus or minus some value, right? Okay? So like for instance, maybe plus or minus 1 standard deviation or plus or minus 2 standard deviations. You want to know what the probability is. Well, you can take the integral of this using the error function. And that's what is expressed in this plot here. If your bound is going towards it's essentially going outwards. So your bound here is going outwards symmetrically. We always integrate with this thing symmetrically. Then the error function gives you a way of computing what the probability is, that is to say, the area under this curve is. Because actually it's not like a nice closed form solution. It's nasty. So the error function is something that we would typically either use computing software like MATLAB to compute the error function for a given value, or we would use a table. So those are the two main ways of doing it. And I believe your textbook has inside one of the covers a chart that looks like this, and then a table of values to look up for what percent you have and how far it goes out in terms of standard deviations. So the usually what's plotted here, they call this the z variable. Okay? And the z variable is also called the z-score. So the z-score, yeah, there are tables for all of it. And also, conveniently, there are MATLAB functions for them too. So you don't have to compute these things yourself. You either look them up in the table, you look them up, or you get them from MATLAB. Now, I am going to go through in more detail and talk about how to do these computations. They're not that hard. But before I let you go, and I am going to let you go in just a sec, I want to talk about this. So for a small sample size, so remember that when you go to a large sample size, the distribution of the means approaches Gaussian distribution, right? We just looked at that. But for a smaller sample size, it's not Gaussian. It's better to use what's called student's t-distribution, okay? As you get to larger and larger sample sizes, it approaches the student's t-distribution approaches the Gaussian. But for low sample size, for reasons that we don't really have time to get into, the student's t-distribution is better. So there's also a t-score and a t-chart that looks a lot like the z-score and the z-chart that is in the textbook as well. So those two things, those two tables, there's also a t-score function, a PDF t, I think it is, or something like that, in MATLAB where you can use that to compute your t-score. So we're going to use z-scores and t-scores to compute confidence intervals, okay? So I think that I gave you guys, like hopefully today, I gave you guys the concept of it and demonstrated that the central limit theorem is valid and that it is normally distributed as you increase n significantly. For lower n, we're going to need the t distribution, and it's safer just to use the t distribution if you're not sure because it approaches Gaussian for high n anyways. So you're never going to go wrong with the t distribution. So I would recommend typically using t distribution. But we'll learn how to do both. Z-score is a little bit easier to work with. T is just barely harder. So I'll do some examples of those for some problems. Your homework has that. So what I'll do is I'm gonna upload a video that's gonna talk about how to do the z-score and the t-score problems on your homework, which is due Monday. So I will make sure I upload a video to make sure you guys can compute those. Not any trouble. I mean, like, these are things that the internet's really good for, these sorts of problems, because a lot of people need to do this. Except business majors, they don't need to do it, but they also don't have our confidence. Yeah, that was also not a planned joke. They never are planned. Yeah.
Is it going to be over Slack for the synagogue?